Today we're going to look at the building blocks for the definition of the definite integral. Now, as we looked at our topic last time, we did most of the things we need to. Today we're going to elaborate and go into a lot more detail and talk about the formal terminology we use as well. In the previous example, we looked at using left and right endpoints to approximate the area, and we started with the function x cubed plus 1 over the x interval from 0 to 2, and we looked at using 4 rectangles and then 8 rectangles as well. In keeping with an equal width. Now, technically, we wouldn't have to keep an equal width. We could make each of the subintervals a different width, but it's so much easier to work with when they are equal width. Now, in working through this example, we had split 0 to 2 into 4 rectangles. We started with 4. And the formal terminology for that is to partition. We're going to set up a partition of our interval from 0 to 2, and we're going to split that up into 4 parts. So our formal notation, we have A, which is always our left endpoint of the total interval, or sometimes we'll call that x sub 0. Then x sub 1 would be the right endpoint of the first subinterval. Then x sub 2, x sub 3, and then x sub 4 will be the very end of our x interval, which sometimes we also call b. Now, partitioning the interval from 0 to 2 with 4 rectangles and using equal width, we came up with these two different sums, okay, the right endpoint and the left endpoint. Notice right endpoint is using x sub 1 as our first function value, then x sub 2, x sub 3, and x sub 4, plugging those x values into the function would give us the height of that rectangle. And in our first example we looked at, we actually used the left endpoint. So we start here, which then means our fourth rectangle would be dealing with an input of 1.5. So x sub 0, x sub 1, x sub 2, and x sub 3 would be our x values used to get the lengths of our rectangles. Now, both of these would be considered sums of estimating the area under this curve, and we choose the endpoints because they're easiest to work with. But we could actually use any point in the subinterval. So the first subinterval from x sub 0 to x sub 1, or in this case from 0 to 0.5, we could use any x value in that interval as our input into the function to get our height for that rectangle. Now, what we have done has given us a little more uniformity, but in the first subinterval, whether we use 0 or 0.5, or we could use 0.4 for the x value there, the second subinterval between 0.5 and 1, we could use 0.75 or 0.98632. I don't know why we would, but we could use that. So any x value in each one of these subintervals can be used as what we call the sampling point. We use that x value to input into the function to get us the height of the rectangles. Now, the left endpoints and the right endpoints are probably the least accurate as far as approximation of area under a curve, but one of the most accurate ones, sampling points, would be what we call the midpoints. Here is the result of using the midpoints of each subinterval. Again, the first subinterval from 0 to 0.5, the midpoint of that would be 0.25. So we plug that into the function to get the height of the rectangle, and then again times the width of that rectangle. Our first rectangle would be the area would be represented by that. Second rectangle, third rectangle, and fourth rectangle. Notice we're using the midpoints here. It would give us more accuracy on our estimate, our approximation of the area, but in this case we don't know whether it's an upper estimate or a lower estimate like we talked about on these two estimates. However, the accuracy would probably be better to have than knowing whether it's an upper estimate or lower estimate. All of these sums are what we call Riemann sums. And the Riemann sum we will use to develop this formal definition of the definite integral. The definition for the Riemann sum of f of x for the partition delta, that Greek letter delta, is where x sub I minus 1 less than or equal to c sub I less than or equal to x sub I. F of x is defined on the x interval from a to b. Delta is a partition of the interval from a to b, given by a, which again is represented by x sub 0, then x sub 1, x sub 2, and in general up to n number of rectangles. And x sub n, again, will be our b value, the last part of our x interval. And the delta x sub I is the length of the ith subinterval. Now, we've been using that saying the width of our rectangle, but delta x sub I would be, well, let's just call it the width of the ith subinterval. So delta x sub 1 would be the width of the first rectangle. Delta x sub 2, the width of the second rectangle. Now, notice these, in this definition, delta x does not have to be the same for each rectangle. Unlike what we were using where we said, let's use equal widths. This would be considered delta x sub 1, delta x sub 2, delta x sub 3, and delta x sub 4. Well, if we keep them equal, we can just say delta x for all the subintervals. Now, in the definition, we will be able to consider the largest of all of these delta x sub i's, okay? And we call that the mesh or the norm. Notation-wise, that is kind of a double absolute value around the Greek letter delta. This is what we call the mesh of the partition, or the norm of the partition, the largest one of the delta x sub i's. In our case, that will be the delta x, the width that we choose, because we do choose equal widths. Okay, now is the time that we've all been waiting for. Drum roll, please. The definition of the definite integral of f from a to b is the limit of the Riemann sum as the lengths, or widths as we call them, of the subintervals approach 0. Now, let's look at that in a little bit more relaxed terms. We'll look at the notation, and then we'll kind of talk through what this means in terms of what we have talked about. So here is the notation for the definite integral. So far we've been looking at integrals, but we've been calling them indefinite integrals, and another word for those would be antiderivatives. This is a different notation. We still have the integral sign, but we have what we call integral limits from A to B. So when we have numbers in those places, this makes it a definite integral, a different operation than what we've been doing up to this point. And the definite integral of f of x dx is, well, this notation here is precisely the summations we've been doing in our estimating the area under y equals f of x, and some of the terminology we've been dealing with. Delta x sub I, that's the widths of the subintervals. Okay, and again, keeping it equal, we can just say delta x. And then f would be our function, and the c sub I represents what we call the sampling point. Now, in our estimations, in our approximations, we would use either the left endpoint or the right endpoint as our sampling point. But in general, we can use any x value in each of the subintervals as our sampling point. Then the more rectangles we have, I talked about this in the previous lesson, basically this would be saying as n approaches infinity, or the mesh is going to 0, since we have equal widths, we can simply say n would be approaching infinity, and that would give us the same limit as the mesh approaching 0. So there we have it. What we've done so far, we have now defined the definite integral of some function from a to b, and in our next video I'll give you a lesson on how to actually go through this, some practical steps. We'll take a look at an example of using the definition to find the value of this definite integral.